Okay. So okay, thank you for coming. I'm Jungmin Park, Junior Research Group Leader at APCTP, and I'll be chairing this today's seminar. This is the first seminar of the APCTP Colloquium series in 2024. And it's my great pleasure to introduce Professor Christopher Jarzynski. He got his PhD at the University of California, Berkeley, and after postdoc at the University of Washington and Los Alamos National Laboratory, he joined the University of Maryland in 2006, and he is now the distinguished university professor of the University of Maryland. And his research interests include the statistical mechanics and thermodynamics in small systems at the molecular level, their application to the problems of biophysical interest, and the analysis of artificial molecular machines, and develop of the schemes for estimating thermodynamic properties of complex systems, and the relation between thermodynamics and information processing, quantum thermodynamics, and quantum and classical shortcuts to adiabaticity. So yeah, he's interested in very lots of interesting topics. Yeah, and he got many important significant awards, including the Lawson Duggar Prize in 2019. And he's known for his equality, the Jarzynski equality, that shows the relation between work in non-equilibrium process and equilibrium free energy difference. And so it was the first relation in the form of equality that holds for non-equilibrium systems. So it led the big birth of stochastic thermodynamics. So I think can be considered as one of the founders of the stochastic thermodynamics. Uh, yeah. Uh, so yeah, now we can start this talk. So yeah, Professor Jarzynski, yeah, please begin.
Okay. Thank you very much for that introduction. I feel very honored to have been invited to give this colloquium. And as we had discussed before starting my talk, please feel free to interrupt with questions during the talk if you have any questions. And the title of my talk is Scaling Down the Laws of Thermodynamics. And I am particularly happy to discuss this subject today because this year marks the 200th anniversary of the publication by the French engineer Sadi Carnot of a pamphlet called Reflections on the Motive Power of Fire. This is a wonderful title. It sounds even better in the original French. And in this title, Carnot is telling us, here are my deep thoughts about how fire makes things move. And the publication of this pamphlet really marks the birth of thermodynamics as a field of scientific inquiry, because it's in this pamphlet that Carnot presents the original statement of the second law of thermodynamics. Now, as you may know, Carnot arrived at his result by considering the behavior of macroscopic machines, notably the steam engine depicted on the left over here. 200 years later, scientists are studying the behavior of microscopic machines like the ATP synthase depicted on the right. The ATP synthase is a beautiful biomolecular complex. It resides in the mitochondria of the cells of living beings, and it generates chemical work, notably the synthesis of adenosine triphosphate. Now, the ATP synthase and many other molecular motors and machines like it are really microscopic analogs of macroscopic machines like the steam engine. So it's natural to ask, how do the laws of thermodynamics, laws that were originally written down to describe the behavior of macroscopic systems like steam engines, how and to what extent and in what form do those laws apply to microscopic systems like the ATP synthase? Or more succinctly, what do the laws of thermodynamics look like when applied to very small systems? Now, I'm not going to be able to give a comprehensive answer to this very broad question today. Instead, in this talk, I will give a brief overview of progress, both theoretical and experimental, that has been made over the past few decades in understanding specifically how the second law of thermodynamics applies to small systems like the ATP synthase. I'm going to organize my talk around 4 new features of thermodynamics that arise at the nanoscale, and I'll describe the new things that we have learned about these novel features over the last few decades. The first of these new features is the prominence of fluctuations. To illustrate what I mean by this phrase, let's start by considering a macroscopic system, an ordinary rubber band. So imagine I take a rubber band, I attach one end to an immovable wall that's shown over here, the other end to an ideal spring, and then this is me at the far end of the spring, kind of pulling with all my might, trying to stretch the rubber band. Imagine that this rubber band is surrounded by a room full of air at ordinary temperature and pressure. And I'm going to let lambda denote the distance between the wall, which is fixed, and the far end of the spring. And I'll think of lambda as a work parameter. This is a variable that I control directly, and by manipulating lambda, I can act on the rubber band. So with these elements in place, I have a system of interest, which is the rubber band attached to the ideal spring. I have a thermal reservoir, that's the surrounding air. I have a work parameter lambda. Now let me imagine subjecting this system to the following irreversible process. I begin in an equilibrium state at lambda equals A. I then stretch the rubber band by changing lambda from A to some greater value, B. And I imagine that I do this relatively quickly. So in doing so, I drive the rubber band out of equilibrium. In particular, a rubber band will get hotter if you stretch it rapidly. Additionally, of course, when I stretch the rubber band, I'm going to perform a certain amount of work on it, and I'll let W denote that work. And at the end of the process, I imagine that I hold the work parameter fixed at its final value, lambda equals B, and I allow the system to come to a new equilibrium state. So I begin in one equilibrium state, A, I end in a different equilibrium state, B. At intermediate times, the system is driven away from equilibrium and work is performed on the system. And the second law then tells us that this work must be greater than or equal to the free energy difference, delta F, between the initial state and the final state. Remember that free energy is a state function, so it has a well-defined value in any equilibrium state. The delta F here is just the difference between the free energy value in the initial state A and then the final state B. So this is what the second law predicts for any process that occurs in the presence of a single thermal reservoir. And throughout this talk, when I'm going to discuss the second law, when I mention the second law, I'm going to mean specifically this inequality. Although I should say that all of the results that I will present can actually be generalized to situations that involve, for instance, multiple thermal reservoirs at different temperatures. Now let's look at a microscopic analog of this situation. And here I have in mind a single molecule pulling experiment. So imagine I take an ordinary strand of RNA, that's this squiggly blue line over here. I use some fancy chemistry to attach the two ends to 2 microscopic polystyrene beads. These are these circles. This entire system is immersed in water. And then I grab one of the beads with a micropipette. This is a tiny suction device. I grab the other bead using a laser trap or so-called optical tweezers. And let lambda denote the distance from the micropipette, which is fixed, to the center of the laser trap. And I can control that. And in fact, experimentalists do these kinds of experiments. And again, then by moving the laser trap, I can stretch or contract the strand of RNA. And I should mention, by the way, that the scale here is completely is way off. In reality, these beads are enormous compared to this poor little strand of RNA that's tethered between them. But this is meant to be a kind of schematic depiction. So let me imagine subjecting the RNA strand to an irreversible process that's analogous to the stretching of a rubber band. So I start with the RNA in equilibrium in some state A. I then stretch the RNA strand by changing lambda from A to B. In doing so, I perform a certain amount of work on the system, and at the end, I allow it to relax to a new equilibrium state B. Now imagine that I go back and do this process, and I repeat this process over and over again, in principle, infinitely many times. Each time I carry out the process, the RNA strand is jiggling around differently just due to thermal motions. And as a result, the amount of work that I perform every time I stretch the RNA strand is going to be different from one repetition or one realization of the stretching process to the next. So in this case, the second law suggests that the average work, W in angular brackets, the average work should be greater than the free energy difference delta F, but now there are going to be some substantial fluctuations around the average just because we're dealing with a very small system. So the kind of semi-quantitative picture that emerges from these considerations is shown over here. In the macroscopic case of the rubber band, we have a sharp value of work. That value must be no less than the free energy difference delta F. In the microscopic case of the RNA strand, we have a distribution of work values. The rho of W, this curve over here, think of it as a histogram of all of the work values that were observed over infinitely many repetitions of this stretching process. As I mentioned, the second law then predicts that the mean of this distribution is greater than delta F, as shown here, but now we have substantial fluctuations around the mean, and in fact, every once in a while, we might even observe a value of work that's less than delta F in this left tail over here. This is something that we would never see for a macroscopic system like a rubber band, and I will return to these events later on in the talk. Let me now generalize this situation a little bit by considering two processes, which I'll refer to as a forward process with the subscript F and a reverse process with the subscript R. The forward process is exactly the same one I've been talking about. We stretch the rubber band by changing lambda from A to B. In the reverse process, I imagine that I start in an equilibrium state B, and then I contract the rubber band by changing lambda from B back to A. And let me assume that whatever schedule or protocol I used in going from A to B during the forward process, I'm going to use exactly the opposite, the time reversed protocol to go from B back to A in the reverse process. So both of the processes satisfy the second law, as shown over here. The minus sign here just reflects the fact that the initial and final states in the reverse process are the opposite of what they were for the forward process. I can then combine these two inequalities into an inequality chain that's shown over here. And this one has a very nice physical interpretation. It says the work that I do during the forward process when I stretch the rubber band must be greater than the free energy difference delta F, and that in turn must be greater than or equal to minus WR, which is the work that I get back from the rubber band when I contract it. So over the course of one cycle of stretching then contracting, I do more work when I stretch the rubber band than I get back when I contract it. And that additional work ends up as energy that gets dissipated into the surrounding thermal reservoir. And you can think of this as a kind of no free lunch theorem, in the sense that if this inequality were the other way around, then over the course of one cycle of stretching and contraction, I would be able to harvest energy from the surrounding thermal reservoir and convert it into work. And if that were possible, then we wouldn't have to, burn fossil fuels to get our energy. Our energy plants would just be enormous buildings filled with millions of rubber bands that were being stretched and contracted and stretched and contracted. The net effect would be to harvest energy from the surrounding air and convert it into work. And of course, the second law absolutely forbids this. In the microscopic case of the RNA strand, it's a very similar situation, except now we have fluctuations. So imagine I take my strand of RNA, I stretch it, I contract it, I stretch it, I contract it over and over again. Every time I stretch it, I measure the amount of work that I do to stretch it. Every time it contracts, I measure the amount of work that I get back when it contracts. And at the end of the day, I construct these two histograms, two distributions of forward work values and distributions of reverse work values, and the means of these distributions satisfy the same inequality chain as the work values did for the macroscopic system. And now, of course, we have fluctuations around the means. So every once in a while, for instance, we might have a process where we stretch and contract the rubber band, and we actually get a little bit of energy out of the system rather than putting it into the system. But on average, over one cycle, we have to put energy into the system in the form of work. So this kind of, again, what I call a semi-quantitative picture was already understood more than 100 years ago by people like Maxwell and Boltzmann and Gibbs, who appreciated the fact that the second law of thermodynamics really is a statistical statement. It's a statement about averages. So what's new? So what's new in all of this? Well, it turns out that these fluctuations in work and in other quantities such as entropy production, these fluctuations satisfy some relatively strong and unexpected laws, and these are sometimes known as fluctuation theorems. I'm going to focus on two of these during this talk, two of these results plus some of their implications and some of their extensions. And the first one is the following. So let's go back for a moment just to thinking about a single process. Let's say the forward process. Here's the distribution of work values. And now, instead of looking at the average value of the work, let's consider the average value of the quantity e to the minus beta w. Here, beta is 1 over the product of Boltzmann's constant and temperature, T, where the temperature here refers to the temperature of the surrounding thermal reservoir. W, again, is the work done in one realization of the process. Angular brackets are an average over infinitely many realizations of the process, or equivalently, they're an average over this distribution of work values. And the claim is that this particular average is going to be equal to e to the minus beta delta F, where delta F is the free energy difference between initial and final equilibrium states. Moreover, the claim is that this is true even if the system is driven substantially far from equilibrium during the process. And if you think about it, this places a relatively strong constraint on the distribution of work values, because you see that this distribution, rho of W, this will depend significantly on how we carry out the process. If we perform the process very, very slowly, so nearly reversibly, we would expect a very sharply peaked distribution of work values very close to delta F. Whereas at larger speeds of performing the process, we get a broader distribution of work values. And this says that no matter how we do it, whether we do it slowly or quickly or at some intermediate speed, this particular average is going to be determined uniquely by the initial and final equilibrium states, because those determine the free energy difference, delta F. Now let's consider a pair of processes, a forward and a reverse process, as I had discussed on the previous transparency. So we have these two histograms, rho f of w, rho r of minus w. And Crookes showed about 25 years ago, when he was a graduate student at the time, he showed that these two distributions of work values satisfy this very nice symmetry property. And again, this property, or this fluctuation theorem, is valid even if the system is driven substantially far from equilibrium during the process. From this fluctuation theorem, one can derive this one in essentially one line. Moreover, this fluctuation theorem predicts that these two distributions of work values are going to cross exactly at the free energy difference delta F, because when W is equal to delta F, the right side of this equation is equal to unity. So as I mentioned, I'm going to focus on these two fluctuation theorems, along with some of their implications and some of their generalizations. But I should emphasize from the beginning that these two are just two out of a broader class of fluctuation theorems, maybe half a dozen to a dozen, depending on how you count, that have been derived over several decades, which have similar structure to these two predictions. Some of this goes back to very early work by two Soviet scientists, Bochkov and Kuzovlov. There was a flurry of activity in the 1990s related to fluctuation theorems for entropy production. A beautiful paper by Gerhard Hummer and Attila Szabo that connected this to the biophysical context, like single molecule experiments. A nice synthesis of many of these results by Udo Seifert into a single kind of thermodynamic framework that we now call stochastic thermodynamics, and I could list other people as well here. So again, I won't have time to discuss these other results, but you should be aware that the two that I'm going to focus on are two out of a broader class of results. Let me move on to some experimental data. So in 2005, this is some experimental data from experiments carried out in 2005. This was an effort led by Felix Retort. He was working in the lab of Carlos Bustamante at the time. And they basically carried out this kind of stretching and contraction process involving a single strand of RNA. So the figure down here shows the raw data, so to speak, from about half a dozen cycles of stretching and contraction. So on the horizontal axis is extension. You can think of that as the distance between the two beads. On the vertical axis is the force. This is the force that's being exerted on this particular bead by the laser trap. And one can measure this force after properly calibrating the laser trap. The orange curves here represent the force versus extension for the stretching portion of the process, and the blue curves are for the contraction portion. And again, this is for about 5 or 6 cycles of stretching and contraction. And what's going on here is the following. This particular molecule, in its native state, it folds into what's called a hairpin turn, or a hairpin fold. And when you start to stretch it, it all of a sudden unfolds. And these diagonal lines here that you see over here and down here are the unfolding of the molecule or the refolding of the molecule when it is contracted. And you see immediately that on average, the area under one of the orange curves is greater than the area under the blue curves. And that's just the second law of thermodynamics in action. It's telling us that it takes more work to stretch the molecule than we get back when we contract it. By repeating this process hundreds of times, the experimentalists were able to measure these work distributions similar to the ones that I had just described. So in the figure on the right here, the two purple curves are the forward and reverse work distributions. They use the labels U for the forward process. U means unfolding, and R for refolding for the reverse process. So this is the forward and reverse work distributions for the wild type molecule. So this is a molecule that was RNA molecule that was harvested from E. coli. And then the two yellow curves that you see in here are also the forward and reverse work distributions for a mutated version of this molecule. And I should emphasize that these two pairs of distributions are just the experimental counterparts of these distributions that I've been talking about up to this point. So then, in order to test Crookes's prediction, which is over here, the experimentalists looked at the yellow curves because those had some overlap. There was some overlap between those two work distributions. In the case of the purple curves, there was not enough overlap to give any statistically significant answer. But in the yellow curves, they looked at this distribution of here, this region here, where there's some overlap between the two curves. And the inset here is for this region from 155 to 160, so roughly where these two curves overlap. And what's plotted here is the logarithm of the left side of this equation. And this is plotted against W in units of KT. So according to Crookes's prediction, this plot should be a straight line with a slope of unity. And the best linear fit gave a slope of 1.06. And this was well within experimental error. So this experiment was one of the early experiments that gave some evidence some empirical evidence in favor of fluctuation theorems. In fact, this was the first piece of empirical evidence in favor of Crookes's fluctuation theorem. Let me jump forward 10 years to what I think was a very exciting development involving quantum fluctuation theorems. So first of all, in 2003, Shaul Mukamel published a paper in which he argued that this fluctuation theorem over here can apply or applies as well to quantum systems under appropriate circumstances. And in fact, similar results had been derived earlier by Jorge Kurchan and independently by Hal Tasaki. Those appeared on the archive, but were never published in journals. And in 2015, this prediction was tested in a collaboration between two groups in Beijing, the theoretical group led by Haitao Quan and an experimental group of Kiwan Kim. And in this experiment, they trapped a single ion of ytterbium in an ion trap. This effectively forms a harmonic potential. So the ytterbium ion, its energy is quantized by the usual formula for the quantum energy levels of a harmonic oscillator. This ion was trapped. The system was brought to equilibrium at a particular temperature, and then the trap was moved from one location to another location at various speeds. Then, by measuring the initial and final energies of the system, the experimentalists were able to empirically measure the amount of work performed in moving this ion trap from one location to another location. And again, they did this at a number of different speeds, at a slow speed, an intermediate speed, and a fast speed. At each speed, they carried the process out many times, so they were able to get distributions of work values. And here are the distributions of work values that they obtained from these experiments. Note that here, these distributions really are histograms because the work values themselves are quantized because the underlying energy levels are quantized. So these are experimentally determined work distributions for this situation involving an ion trap. And in this particular situation, the free energy difference delta F is equal to 0. Therefore, the theoretical prediction states that the average of E to the minus beta W should be equal to 1. And when the experimentalists then evaluated this average from their data, they found that in each case, the average of the average of E to the minus beta W was equal to 1 within statistical error. This experiment, as well as another one that was performed roughly at the same time using an entirely different approach, they provided the first experimental evidence in favor of quantum fluctuation theorems. And by the way, whatever you happen to think about the theoretical predictions, I find it exciting that experimentalists these days can actually go and measure the work performed on a single quantum system, like a single ion of ytterbium trapped in an ion trap. So over the years, over the past couple of decades, a number of experiments have been performed, mostly in the classical realm, but some quantum ones as well. A number of experiments have been performed to test these and other fluctuation theorems using a variety of physical platforms. I've just listed a few of them over here. A mechanical oscillator, a single trapped colloidal particle, the unfolding of the giant protein molecule, titin, a single electron box. Despite the name, the single electron box is effectively a classical system. It's not really a quantum system, and a number of other physical platforms. I won't go into any of these other experiments in detail, but I will mention that to date, all of the experiments have yielded results that are in agreement with the theoretical prediction. So I believe it's fair to say that at this point, there's a reasonably large body of experimental evidence suggesting that these fluctuation theorems, as well as others, are in fact valid. So in other words, over the past few decades, we've learned, both experimentally and theoretically, that when fluctuations are properly accounted for, then the relationship between work and free energy in small systems that are driven away from equilibrium, that relationship can be expressed in terms of equalities rather than inequalities, the equalities like these fluctuation theorems shown over here. So in some sense, these equalities tell us what the second law of thermodynamics looks like for these very small systems driven away from equilibrium.
I have
So,
one question.
yes, please.
In the case of the first quantum experiment, how did they estimate work or e to the minus w?
So, in order to evaluate the work, what they had to do is they prepared the system in equilibrium. So they prepared it in a statistical state that reflected that reflected a Boltzmann distribution at some particular temperature. And then their experimental setup allows them to make a projective measurement of the energy of the system. So they made a measurement of the initial energy of the system, and this projected the system onto a particular energy eigenstate. Then, starting from that energy eigenstate, they moved the trap. The system evolved under the time-dependent Schrödinger equation, and at the end of the process, they made a second projective measurement of the final energy. And in this case, there was no thermal reservoir involved during the process. So the argument, and the argument really goes back to these theoretical papers, the argument then is that in that situation, the work should just be the difference between the initial measured energy and the final measured energy. And the experimentalists just took that difference, repeated the process many times, and then that's how they were able to construct these histograms.
Nice, thanks.
Okay, thanks. Thanks for the question.
Um,
Okay,
so,
yes?
Yeah. Is there any experiments which use the other general measurements, like the non-demolition measurement or general POVM?
I don't, I'm not aware of other experiments that use POVMs in this case. To be perfectly honest, so I mentioned this quantum fluctuation theorem that was derived in these papers. This holds for the special case where there's no thermal reservoir involved. What this theorem should look like in the quantum case when there are thermal reservoirs is really not yet known. So that's a separate comment, but I'm not aware of experiments involving POVMs. I did mention another experiment that was done around the same time, but that involved a kind of interferometric way of measuring the systems, interferometric way of measuring the energy distribution. So this involved, I don't remember the details, but roughly speaking, you entangle the system with some kind of ancilla system. Then by making measurements on the ancilla, you can get you can measure the Fourier transform of the work distribution. And then by taking the Fourier transform back, you can get the work distribution.
So usually, I mean, up to now, the quantum equality is only, okay, so studied for the project measurement cases.
That's right. It's for projective. I mean, there is quite a lot of work going on into trying to extend these results to other scenarios, but I don't think that any kind of quite as clean results as these have been derived for non-projective measurements. But I should think about that because often I forget some of the work that's out there, and I haven't always followed all of the literature. All right, so as I was mentioning, these results in some sense represent what the second law looks like for very small systems. And speaking of the second law, let me now move on to the second feature of thermodynamics at the nanoscale, and these are so-called violations of the second law. And I'm always going to put the word violations in quotes here because I'm not suggesting that the second law is in any way overthrown. This just happens to be this term just refers to the fact that in small systems you have relatively large fluctuations, and I'll explain that what I mean by that in a moment. First of all, let me point out that this equality, which is a physical prediction, mathematically, this implies two inequalities that are shown over here. The first of them is just that the average work is greater than the free energy difference. So this inequality follows from this equality just due to the fact that that the exponential function is convex. Its second derivative is always positive. So what this means is that it's nice to see that this fluctuation theorem is not only is it consistent with the second law, in fact, in some sense, it implies the second law. Now let me move on to the second inequality, and for that, let's focus on these so-called violations of the second law. So when I say violations of the second law, what I mean is any event where the work is less than the free energy difference, delta F. And again, this is a term that's become popular in the literature, but everybody understands we're not suggesting that the second law is in any way overthrown. But for a small system, every once in a while, you might observe a value of work that's less than the free energy difference delta F. And so if such violations, in quotes, if such violations can exist, and if we'd like to have a thermodynamic theory of very small systems, it would be nice for that theory to tell us something about these violations. How frequently can we expect such violations? How large can these violations be? And so forth. So let me first ask the following question. What is the probability that the second law is violated by at least an amount zeta? And to explain what I mean by this question, let me zoom in on this left tail of the work distribution. So here it is. So all of the work values to the left of delta F are these so-called violations. And when I ask what's the probability that the second law is violated by at least zeta, I mean, if I perform the experiment once, what's the probability that I will get a value of work that's no greater than delta F minus zeta? In other words, what's the probability of getting a value of work up to this point, delta F minus zeta? So that's the area underneath this curve. And from this equality, one can derive, again, it's a derivation that takes 3 or 4 lines. One can derive the following inequality. The probability of observing a work value no greater than delta F minus zeta. This probability itself is bounded from above by e to the minus zeta over kt, where zeta can be any positive number. We can choose zeta to be whatever we wish.
So I have one question. So
Yes.
if zeta becomes 0, then this inequality tells us that the probability W is less than delta F. That there is inequality, not equality. I see.
Inequality, yeah. And
I
I will actually get to that. I will get to that exact point in just a moment. So first of all, let's consider some finite positive value of delta. What this is saying is that the area underneath this portion of the tail decays exponentially or faster as we move into this thermodynamically forbidden region of the tail. So for instance, this says that we might have some chance of observing a violation of the second law by 2 kt or by 3 kt, because e to the minus 2 and e to the minus 3, those aren't really very, very small numbers. On the other hand, we have no hope whatsoever of observing a violation of the second law by 100 kt. Even though 100 kt would be a really tiny, tiny violation on the macroscopic scale, e to the minus 100 is such a small number that for all practical purposes, it's equal to 0. So this puts a very, very tight bound on observing any large violations of the second law. And this is in agreement with our everyday experience, because in our everyday experience, the second law isn't just satisfied on average, it's always satisfied. Okay, so this puts a tight bound on large violations of the second law. But now let's suppose we want to know something about what's the probability of observing any violation of the second law. So let me set zeta equal to 0 plus. By this, I mean some number that's infinitesimally larger than 0. And then if I plug this zeta into both sides of this equation, I get that the probability of having the probability that W is less than delta F, that probability must be strictly less than 1. In other words, what this is telling us is that we can't have a situation where the entire work distribution is to the left of delta F. But that isn't telling us anything new, because that scenario is already ruled out by this inequality. So even though this puts a very tight bound on the probability of observing large violations, effectively it places no bound at all on the total probability of observing a violation of the second law. So this raises the possibility, is it possible to have a process where, let's say, more than 50% of the time the second law is violated, or maybe more than 90% of the time the second law is violated? This was investigated experimentally about 5 years ago in Jukka Pekkala's group in Finland using a single electron transistor. Again, this was effectively a classical system. It's not a quantum system. I won't go into the details of the process they carried out, but here are the results. So this plot shows the distribution of work values. And this is not 2 different distributions. This is one distribution that happens to be bimodal. It has 2 peaks. There's a peak over here and a peak over here. In this particular experiment, the free energy difference, delta F, is equal to 0. So all of the work values to the right of 0 are consistent with the second law. All of the work values to the left of 0 are these so-called violations of the second law. And you can see by eye that the area underneath the left peak is greater than the area underneath the right peak. In other words, more likely than not, you get a violation of the second law. However, in fact, in this particular experiment, the probability under this left curve was about 2/3, and the probability under the right curve was about 1/3. So in other words, here we have a process where when you carry it out many, many times, more than half of the time, roughly 2/3 of the time, you get a violation of the second law. However, on average, the work is still greater than the free energy difference, delta F. Here's the actual value due to the relative placements of these two modes of the distribution. So in other words, what we've learned in the last few decades, and again, both theoretically and experimentally, is that there are very tight bounds on the probabilities of observing violations of large violations of the second law, but no real bound on the net probability of observing violations of the second law. In fact, we can have these very counterintuitive situations where most of the time we observe violations of the second law. Let me now move on to the third feature of thermodynamics at the nanoscale. And I'll refer to this as the blurred arrow of time. And to illustrate what I mean by that, let me look at this nice little cartoon that's taken from a paper written by Joel Leibowitz over 30 years ago about the second law of thermodynamics. This cartoon illustrates the English nursery rhyme of Humpty Dumpty. So whether or not you're familiar with that nursery rhyme, Humpty is this vaguely creepy egg-like creature that's sitting on a wall over here. And in the nursery rhyme, Humpty Dumpty falls off the wall. He breaks because Humpty is an egg. And according to the nursery rhyme, all the king's horses and all the king's men couldn't put Humpty together again. And this nursery rhyme is a kind of parable for the familiar concept from everyday experience that events happen in one direction and not in the opposite direction. So I'm pretty sure everybody on this Zoom call has at one point or another seen an egg falling down on a hard surface and breaking. But I'm much, much more certain that nobody on this Zoom call has ever seen a broken egg spontaneously jump up and put itself together again. In fact, if I were to show you a movie of an egg that starts out broken and then puts itself together again, you would immediately know that without thinking about the second law, you would immediately know that you're seeing a movie that's being run backward in time. So this is what's normally known as the arrow of time. And it's also known that this arrow of time is very closely related to the second law of thermodynamics. Namely, it points in the direction of increased entropy. So the reason we can go from this situation to this situation, but not the other way around, is that when an egg breaks, the entropy of the universe increases. All right, so all of this is well known, but this becomes a little bit more subtle or blurred when we get down to very small systems. So let me explain this in terms of a hypothetical guessing game. So suppose I show you a movie, and in this movie, you see a thermodynamic process where some parameter is being changed from A to B. So for instance, let's say in the movie, you see a single molecule that's being stretched. And suppose for the sake of argument that in this movie, you can see how every single atom is moving around at every instant in time. You have full microscopic knowledge of what's going on, except for one point. Your task is to determine whether you're viewing the events in the order in which they actually occurred, or as a movie that's run backward of the reverse process. In other words, did I actually stretch the molecule and now, I'm proud of what I did, so I made a movie and I'm showing you the movie? Or alternatively, did I actually contract the molecule, and because I have a devious nature, I want to trick you into thinking that I stretched the molecule, so I run the movie backwards? For a macroscopic system, and usually it's pretty easy to tell whether a movie is being run forwards or backwards. But for a microscopic system, it's not so easy. So it turns out that this kind of guessing game can be analyzed quantitatively using the mathematical tools of statistical inference. So we have two hypotheses. One is that the molecule was in fact stretched, and you're seeing a movie of what actually occurred. Let me call that the forward hypothesis, F. And then there's the reverse hypothesis, which is that I contracted the molecule and now I'm running the movie backward in order to make you think that I stretched the molecule. By analyzing this quantitatively, using basically the same tools that Crookes did in deriving his fluctuation theorem, one can show two things. First of all, the only piece of information that allows you to make the best guess of which hypothesis is correct is the work that's performed on the system in this movie that you see. Once you know how much work is performed on the system in the movie, no further microscopic information can allow you to make a better guess as to whether the forward or the reverse hypothesis is correct. Moreover, quantitatively, it can be shown that the likelihood that the forward process was performed, given the work that you observe in the movie, is given by this very simple formula. And this is the logistic function. We know what it looks like. It's plotted over here. This formula tells us that when the work is much greater than the free energy difference delta F, namely when we have a work value that's very strongly consistent with the second law, then the likelihood that the forward process is carried out is very, very close to unity. On the other hand, when the work is much, much less than the second law, when we have a large violation of the second law, sorry, when the work is much, much less than delta F, when we have a large violation of the second law, the likelihood that the forward process was carried out is very close to zero. In that case, it's almost certain that it was the reverse process carried out. And this predicts that there is a universal transition from this behavior to this behavior over a regime of a few KT. And in effect, this theoretical prediction quantifies our ability to determine the direction of time's arrow. Remember, or keep in mind that if we were to plot this plot on an axis where we expressed work in macroscopic units like joules or ergs, then this would become effectively a sharp step, and that's just the second law of thermodynamics. For small systems, this becomes smoothed out in this kind of universal way. So this predicts that there's a universal, this quantifies universally our ability to determine the direction of time's arrow. And a few years in experiment, I should mention, this was first derived by Paul Schertz and colleagues, Michael Schertz and colleagues, and independently by Paul Maragakis and colleagues in a slightly different context involving free energy estimation. This relation to guessing the arrow of time is described in this review article that I wrote a little bit more than a decade ago. And several years ago, an experiment was carried out in the group of by Andrea Hoffman in the group of Klaus Enslin in Zurich, where they took a quantum dot. So again, despite the name, the quantum dot here is really just a classical system. So this is the quantum dot is this small area on the surface of a semiconductor. And because of the way it's constructed, this area is able to accommodate either one excess electron or zero excess electrons. It can't accommodate more than one excess electron. And by changing the voltage on one of these leads that's shown over here, we can make it thermodynamically favorable for there to be one electron or for there to be zero excess electrons. So the experimentalists then carried out a process where they varied this voltage from some negative value, let's say -8, to a positive value, +8, and then back to a negative value, back to positive, and so forth. And in this way, they were able to attract an electron into the quantum dot, and then to push it out of the quantum dot, and then to attract it in and push it out, and so forth. And by measuring whether the electron was in the dot or out of the dot, they were able then to determine how much work it took to bring the electron in and how much work it took to push the electron out over many cycles of bringing it in and pushing it out. And in this case, the bringing in and pushing out of the electron corresponds to the forward and to the reverse process. So by carrying out this such cycles many, many times, and then measuring the work values, the experimentalists were able to empirically reconstruct this likelihood function. And here are the results. So the various circles, squares, and triangles that you see over here These are the experimentally determined likelihood function, L of F given W. The red curve here is this logistic function shown over here, and there are no fitted parameters. And you can see that the experiment and theory agree quite well. The different symbols reflect different experimental parameters that were used. So again, we've learned theoretically and experimentally that indeed our ability to determine the direction of time's arrow can be quantified. All right, that brings me. No, before then, let me briefly talk not about guessing the arrow of time, but about learning the arrow of time. So this is a paper based on a numerical experiment that was carried out by a very bright student, Ali Reza Saif, who was working with my colleague Mohammed Hafezi at the University of Maryland. And this involved machine learning. So here what happened is a large number of trajectories were simulated of a particular forward process, and also a large number of trajectories of a reverse process were simulated. These trajectories then were fed into a machine learning algorithm where the algorithm was told which of these trajectories are forward processes, which of these trajectories are reverse processes. And the algorithm then was trained to try to determine what's a forward trajectory and what's a reverse trajectory. After the training was done, the algorithm then was fed a number of new trajectories that it hadn't seen, and each of these new trajectories either came from a forward process or from a reverse process, but now the algorithm was not told which one it came from. And the algorithm then tried to guess whether it was observing a forward or a reverse trajectory. Moreover, the algorithm estimated what's the likelihood that it is a forward trajectory rather than a reverse trajectory. And after this training, the results are shown over here. So here the kind of blurry gray, which you see in this blurry gray region over here, that's many trajectories. And for each trajectory, the algorithm estimates whether that trajectory is coming from the algorithm estimates what the likelihood is that this trajectory comes from a forward process. And that likelihood is then plotted as a function of the work, W. But the algorithm was not told anything about work. The algorithm was just fed these trajectories and then it was trained to distinguish forward from reverse. And you see that the likelihood functions that this algorithm comes up with really match quite well with the theoretical prediction that's shown over here. So in some sense, this machine learning algorithm, which was simply trying to learn how to detect forward from reverse trajectories, just like these algorithms can detect what is a picture of a dog versus a picture of a cat, through that kind of training, the algorithm effectively was able to come up with this formula, or at least approximately able to come up with this formula. So in some sense, this was learning about the arrow of time all on its own. Okay, let me move on to the fourth and last nanoscale feature of thermodynamics that I want to discuss. And this involves information as fuel, so to speak. To describe what I mean by this, let me first look at the process of measurement and feedback in macroscopic systems. And specifically, let me go back to a steam engine. So imagine I have steam coming in here from a boiler. It comes into a steam engine. That engine then generates some rotational motion. And the problem is that if you don't perform any kind of feedback on this, then it's very hard to maintain a uniform pressure in the steam that's coming from a boiler. So without any kind of feedback process, this steam engine is likely to be very erratic. In other words, the rotation will sometimes go faster, then sometimes slower, and so forth. And you can imagine that for technological purposes from 200 years ago, like textile mills or something like that, this would be bad to have an erratic steam engine. So toward the end of the 18th century, James Watt and Matthew Boulton invented in this context what's called the metal sphere governor. And that's a device that's shown schematically over here. These two spheres are two metallic spheres. They're attached by rigid rods to a central shaft, and they can rotate around this shaft. Hello? Okay, and the rotational motion generated by the steam engine is then converted into rotational motion of these metal sphere governors around the shaft. So the idea is that if the steam engine starts going too fast, if the rotation is too fast, then these spheres start rotating very fast. Centrifugal force then pushes them up, and when they get pushed up, they're connected to a valve that gets closed off. So when they get pushed up, the valve gets closed off, and the steam supply is reduced. Similarly, if the steam engine starts going too slowly, the metal balls drop, and then the valve opens up, and more steam is allowed in. So there's this kind of negative feedback, and you can imagine that if you do the tinkering correctly, then this can produce more or less uniform rotation generated by the steam engine. And in fact, these so-called metal sphere governors or centrifugal governors were a very important component of early steam engine technology. These days, you can go onto Amazon and buy a little model steam engine, and you can see it has one of these metal sphere governors on it. So my purpose in describing this is that I'm going to refer to this kind of feedback control as autonomous feedback control. And by the word autonomous, I just mean that this feedback control is being carried out by some physical gadget. It's a device that was devised for this purpose. I'm going to contrast that with non-autonomous feedback control. In non-autonomous feedback control, I assume that instead of some physical device, there's some external agent, unspecified external agent. It could be me, it could be one of my students, it could be some hypothetical creature. This agent has certain powers of observation. It observes the spinning of this wheel. If the wheel goes too fast, then the agent closes the valve a little bit. If it slows down, the agent opens the valve a little bit. And in this way, the agent tries to get the same kind of control over the motion of the steam engine that the metal sphere governor did in this case. So I will refer to this as non-autonomous feedback control. And this distinction between autonomous and non-autonomous is a little bit artificial because, of course, in reality, any external agent, even if it's a person, is going to be some physical object. But it's useful to keep this distinction in mind when we now go down to the nanoscale. And this finally brings us to the so-called paradox of Maxwell's demon. Over 150 years ago, Maxwell described in a letter to his friend Peter Tate the following thought experiment. He imagined that there's a box containing gas. The box is separated into two portions by a partition. In the left half of the box, the gas is hot. In the right half of the box, the gas is cold. The partition has an opening, and the opening has a trap door. And Maxwell then imagined a hypothetical creature that we now call Maxwell's demon that observes the motions of the gas molecules on both sides of the partition. Now, on average, the molecules here are moving faster than the molecules over here, of course. But still, there's going to be a distribution of speeds here and a distribution of speeds here. So whenever this demon sees an unusually slow particle moving from the left to the right, it opens up the trap door to let that slow particle go through. And whenever it sees an unusually fast particle moving from the right to the left, it opens up the trap door to let that particle go through. So in this way, we get an accumulation of fast particles on the left, an accumulation of slow particles on the right, or as Maxwell put it much more elegantly, the energy in A is increased and that in B diminished. That is, the hot system has got hotter and the cold colder, and yet no work has been done. Only the intelligence of a very observant and neat-fingered being has been employed. Notice that Maxwell talked about the intelligence of some external agent, this neat-fingered being. So Maxwell here was thinking about non-autonomous feedback control. And Maxwell was making the point that if we had an agent that could perform feedback control at the level of thermal fluctuations, then effectively that agent could beat the second law of thermodynamics. Because here, by carrying out this kind of feedback control, the agent is increasing a temperature difference without doing any work. And that's a violation of the second law. So for that reason, this is sometimes described as the paradox of Maxwell's demon. But from a logical perspective, it should be clear that there's no real paradox here. If you put a magical creature into your thought experiment, you shouldn't be surprised if various laws of physics are violated. However, this naturally leads to the following question. Is a mechanical Maxwell demon possible? In other words, in principle, maybe not yet in practice because our technology isn't good enough, but in principle, could we devise something analogous to the centrifugal governor? In other words, could we devise maybe some tiny robot that would operate in the way that Maxwell's demon operates? And if such a device were created, would this constitute a real violation of the second law? This question has been considered for more than 100 years. Smoluchowski discussed it in 1912. Feynman discusses it in a beautiful portion of the Feynman lectures. And both Smoluchowski and Feynman give the answer no. It's not possible to create a mechanical Maxwell's demon, basically because that would be a real violation of the second law. On the other hand, starting in the early 60s and going through the early 80s, in work by Rolf Landauer and Charles Bennett in the United States and Oliver Penrose in the United Kingdom, a somewhat more subtle answer emerged, and I'll refer to that answer as yes, but. So roughly speaking, what Landauer and Penrose and Bennett argued was that in principle, one can make a device, an autonomous device, purely physical device that operates like Maxwell's demon. However, there's a price that must be paid. If this is a real physical device and not some kind of hypothetical agent, if this is a real physical device, then that device gathers information about its surroundings, and that information must be stored in some physical memory register. So we can imagine, for instance, that there's a sequence of bits. Let's say they're all initialized in the 0 state. These bits move past this device, and the device then writes down information onto this bit stream where this information encodes the information that the device gathered in the process of making these measurements. And then what Landauer and company argued is that the increase in the Shannon entropy of this bit stream should count as genuine thermodynamic entropy. So the increase in the entropy over here can compensate for the decrease in the entropy that goes on over here. And in this way, the second law is ultimately not violated. So in other words, this explanation and indeed Maxwell's original thought experiment really tell us that in some sense information, at least information that's gathered at the level of thermodynamic fluctuations, can be used as a kind of fuel, or more generally as a kind of thermodynamic resource, because by gathering such information, we can carry out tasks that otherwise would require us to perform work. And Landauer then additionally argued that this implies that in order to erase information, one must expend a certain amount of work, which gets dissipated as heat into a thermal surroundings. And in particular, Landauer argued that that the amount of work that, the amount of heat that must be dissipated in order to erase one bit of information must on average be kT times the natural log of 2 if this erasure process is carried out at a temperature T. Again, Landauer made this prediction in 1961. It took just a little over 50 years before it was actually verified experimentally, but indeed it was verified in a paper published in 2001. This was an experiment carried out by Sergio Ciliberto's group in Lyon, France, in a collaboration with Eric Lutz, who was a theorist from Germany. And in this experiment, the experimentalists created a kind of double well potential in which they trapped a single particle, and then they effectively erased information this particle could be in either the 0 or the 1 state, and they effectively carried out a process that forced the particle to go into the 1 state. In that way, they were erasing the information in the particle. They carried out this process at various speeds. So here on the horizontal axis is the time tau required to erase the information. And you can see that at higher speeds, the amount of heat that's dissipated in units of kT is relatively large, but as one goes more and more slowly, more and more towards the reversible limit, one approaches a particular value which is consistent with the value of the natural log of 2. And this equality here really should be an inequality. In other words, they predict that the amount of heat that must be dissipated should be at least kT log 2 per bit. So this was the first experiment that verified Landauer's principle about the erasure of information, and other experiments have been performed since then using other systems, and they've come up with the same result. Okay, so finally, I'm on the second to the last slide here. Finally, let's bring this back to single molecule pulling experiments. Let's imagine a situation where we have a single molecule pulling experiment, only now there's some agent. So this is back in the context of non-autonomous feedback control. We have an agent who is continuously measuring the motion of this bead in the trap, and the agent is using that information to perform feedback on the trap. In other words, maybe depending on the outcome of those measurements, the agent might move the trap a little bit faster or a little bit slower. And let's imagine that the goal of the agent is to stretch the molecule using as little work as possible. I'm going to let capital I denote the information that's gained by the measurement during one stretching process. This can be quantified using a quantity that's known as mutual information. And this sort of setup was analyzed quantitatively by Takahiro Sagawa and Masahito Ueda. And in 2008, they argued, using very general arguments, that in this kind of situation involving measurement and feedback, the second law of thermodynamics, which normally would say average work is greater than or equal to delta F, the second law should now be replaced by the following inequality: average work is greater than or equal to delta F minus KT times the average information. In other words, by gaining information about the system, we're able to reduce the amount of work that it takes to stretch the single molecule, or effectively, we're able to beat the second law by gathering this information. And this is really very similar in spirit to what Maxwell was describing 150 years ago, but this is now much more quantitative because it quantitatively relates the amount of work we perform to the amount of information that's gathered. 2 years later, Sagawa and Ueda replaced this inequality with a stronger equality. So this is a fluctuation theorem for situations involving measurement and feedback. And then a number of experiments have been done to test this prediction, including the two that I've listed over here. And let me now just finally, very briefly, look at the results of this experiment by Koski et al., performed in 2014. So this involved a single electron box. The free energy difference here was equal to 0, so the right side of this equation is equal to 1. And without going into details of the experiment, the experimentalists carried out many such processes at different values of a parameter epsilon, where this parameter epsilon reflects the error that's made in the measurement, the measurement error. And what's plotted here in these black points is just the average of e to the minus beta w. And you can see here that this is not equal to unity, and it shouldn't be, because this is the situation where measurement and feedback are being applied. So the ordinary fluctuation theorem should not work here, and it doesn't. But when we look at Sagawa and Ueda's fluctuation theorem and calculate the average of e to the minus beta w for using exactly the same experimental data, we find that it indeed, in this case, is equal to unity within experimental error. So through this kind of interplay between theoretical prediction and experimental tests, such as this one and others, we've gained a really subtle and, in my opinion, a deep understanding of the relationship between work, information, and free energy in very small systems that are driven away from equilibrium. Okay, so with that, let me come to my final slide, my summary slide. The kind of take-home message of this talk is reflected by these two figures that you see up top. In macroscopic systems, values of work and other quantities like entropy production tend to be sharply defined, as shown over here, like discussed for the rubber band. For very small systems, these work values are represented by distributions because the work values represent fluctuations. There are fluctuations in these work values. And when these fluctuations are properly accounted for, then the inequalities that we ordinarily associate with the second law can be replaced by even stronger equalities. And I focused on two of these equalities or fluctuation theorems over here in this talk, but there are a number of others, as I mentioned. I just didn't have time to go into them. And I would say that these fluctuation theorems, both the ones that I discussed and the ones that I didn't, really tell us new information about what the second law of thermodynamics looks like at the nanoscale. And I've also investigated the consequences or extensions of these results for in the context of violations of the second law, determining the direction of time's arrow, and what the second law looks like in the context of measurement and feedback when information can be effectively used as fuel or as a thermodynamic resource. So if you'd like to learn more about this, I can recommend some review articles. Shamelessly, I can recommend my own review article for classical fluctuation theorems and related results. There's a very nice colloquium in the Reviews of Modern Physics by Campisi, Henge, and Tauchner about the quantum version. And Takahiro Sagawa wrote a review article about the information processing aspects that I've discussed toward the end of the talk. All three of these review articles by now are more than a decade old, so they don't contain the latest results. This is a field that keeps evolving. Nevertheless, they give you a good introduction to this field. So with that, I'm going to conclude my talk. I will thank you for your attention. I will be happy to take any questions.
Thank you. Thank you for a very great talk, Mr. Jarzynski. And now we can have the session for the questions. Any questions?
Professor, I have a simple question. So, as far as I remember, there was a slide. There are two peaks on the work probability distribution. And paradoxically, we observe the breakdown of the second law.
Oh, yeah, I know which one you're talking.
1/3 and 2/3. Yes.
Yeah, let's see. I don't know how to get out of my yeah, this one.
Yeah, I'm not sure, but in this case, if we do the hypothesis gaming you mentioned, then we likely to observe the opposite direction. I mean, to determine the process is observed. I'm sorry, the process is reversed.
Well, let's see. Remember that the likelihood function depends on the work that you see, right?
Yes.
So if you see a value of work that's, let's say, 0.25, right, then that prediction that I had about the likelihood function tells you that more likely than not, you are seeing in a movie, you're seeing the process being carried out. You're seeing the forward process. If you see a negative value, you're more than likely than not seeing the reverse process. So I'm not sure that I'm addressing exactly your question, because maybe I'm not sure what you're. Maybe can you repeat the question?
So I'm also not quite sure what I'm asking.
Okay. Yeah.
So yeah. Yeah.
Yeah, I would have to think about that a little bit more carefully, but I believe that result is very general, so it should still apply over here. But it would be very interesting to look at how that applies specifically to this context. But
Okay.
it should still work here.
Okay, and I have a very simple one question. So at the very beginning of your presentation, you mentioned the the stretching,
Yeah.
rubber band stretching
Yeah.
experiment. So when you define the reverse process or backward process, the initial state of the reverse process is the equilibrium state
Correct.
with lambda equal b.
Correct.
So it sounds a little bit, I'm not sure. So what if we set the initial state of the reverse process as the final state of the forward process, which is not a equilibrium state?
Oh, I see what you're saying. So, okay, so the way that I described it, I assumed that the system always comes to equilibrium at the end because I hold value of lambda fixed at the end of the forward process. But one could do a situation where the forward process, you go from an initial equilibrium state to a final non-equilibrium state. And then for the reverse process, you go from that non-equilibrium state back to the initial equilibrium state. So fluctuation theorems have been derived in that situation as well. And these fall under this kind of broader umbrella framework that was developed by Udo Seifert. So in that case, it's probably more convenient to describe the fluctuation theorem in terms of entropy production, but you do get fluctuation theorems in that situation as well. They're just a little bit different from the ones that I've been discussing.
So people already discussed a lot for that
People
case.
have discussed that to some extent, yes.
Okay, thanks.
Sure.
I have one question.
Yeah.
So is there a simple explanation about how to derive that highlighted inequality from your inequality?
Oh,
Yeah.
a simple it's let's see, it's a few lines long, but basically you write this down. This is equal to, let me go back, it's easier to see here. So this thing is equal to the integral from minus infinity up to this point of rho of W, correct?
Yes.
Now notice that over this entire region of integration, W is less than delta F minus zeta. So I can say that that integral is less than the same integral where now I multiply the integrand by e to the beta W minus delta F plus zeta, or something like that. Maybe I have to do it the other way around. So inside the integral, I multiply the integrand by e to the minus beta W minus delta F plus zeta. Sorry, I can't do it in my mind, but you do it that way. Then you pull the constants outside of the integral, extend the region, the upper bound of integration up to infinity. That gives you another less than sign. And then what you've got left is the integral of e to the minus rho of W e to the minus beta W, is that is equal to e to the minus beta delta F. So it's difficult to describe in words, but in an equation is just one line. If you send me an email, I can point you exactly in the review article that I wrote in annual reviews of condensed matter theory in 2011. The derivation is there, and like I said, it's just a few lines.
I see.
I think formally it's an example of what's called a Chebyshev inequality, but you don't need to know that in order to derive it.
Thanks.
Okay.
Any other question?
I have a question.
Mhm.
The fluctuation theorems are expressed in terms of the Helmholtz free energy, and that of course makes sense because you control the position. If you control the force, will you simply replace the Helmholtz free energy by the Gibbs free energy, leaving everything else unchanged?
So to be honest, I've written Helmholtz free energy. Other people write Gibbs free energy for exactly the same fluctuation theorem. So if you look at the single molecule experiment papers, they say delta G, not delta F. The difference between delta F and delta G is very well defined for macroscopic systems because macroscopic systems have well-defined volumes. So remember, the difference is just pressure times volume. For a microscopic system, like a single molecule, it's not entirely clear what is meant by the volume of the molecule. So I would say I use delta F just because I do it by habit. Other people use delta G. It's the free energy here is being defined by the partition function ultimately. And for such microscopic systems, it's not clear what the distinction between Helmholtz and Gibbs free energy is in the first case. There are papers where this is discussed at length.
The difference in the context of these small systems.
Yes, in the context, exactly in the context of these small systems. Yeah.
Can you tell me?
So I have a paper from 2017 in Physical Review X.
Okay.
Don't remember. If you can't find it, please feel free to send me an email. Yeah, so I think some people use delta F, some people use delta G. Everybody agrees on how the free energy is defined because it's defined in terms of a partition function. People may just disagree on whether we should think of it as a free energy, Gibbs or Helmholtz free energy.
Okay, thank you.
Yes, it's a very subtle question.
Actually, I also have one question about the experiments of the RNA folding system. So in that plot, it seems that the fluctuation of the work distribution in backward process is much smaller than the fluctuation of the forward process. And also in your schematic plots, I can see that. So is it just coincidence or there is any fundamental reason for that relation between illustration?
No, because it's just a coincidence. Because in fact, you can choose which process to define as the forward and which process is to define as the reverse. So I could have taken contraction to be the forward process and stretching to be the reverse process. And then basically this schematic curve would look the same, like its mirror image. So in that case, the forward process would have smaller fluctuations and the reverse process would have larger fluctuations. So you can choose either of the processes to be defined as the forward one, and then the other one is defined as reverse.
I see. But what if we define the forward process that has the positive mean value of work, then
Pardon me?
I mean, in this examples, we always take the forward process, which it has the positive mean value of work, right?
So, okay. So the forward process, okay, so let's assume delta F is 0 because otherwise, let's assume delta F is 0, right?
Okay,
so you're saying the forward process has a positive mean value of work, right?
Yeah. So my question is, what if we specify the forward process in that sense, then can we show the kinds of the order between the fluctuation of those processes?
Wait, hold on a second. The forward process has a positive mean work value, right? So does the reverse process. Because the reverse process, what I'm plotting here is rho r of minus W. So if I were to plot rho r of W, the mean value of the work for either the forward process or for the reverse process is always greater than the corresponding free energy difference. So the inequalities are, let me go, whoops, I went back too far. The inequalities are over here.
Right.
Okay. And for small systems, you're going to have average. But other than that, yeah. Okay.
I see, I see.
Okay.
Thank
Thanks
you.
for the
Yeah.
question.
And any other question? Actually, I also have one more question about the Maxwell's demon.
Okay.
According to the bound for the violation of second law, if we
Mhm.
have macroscopic system, then okay, say we have to wait very long time to observe the violation of second law.
Mhm.
So in that sense, even though the Maxwell demon can have very large information, it has to wait very long time to make the violation of second law, right? So maybe we can find some kinds of time limits of to realize the kinds of the broken second law. So is it possible or
I don't know. I haven't seen that. I think that may have been investigated, but I'm not very familiar with that. Let's see. I think there have been some theoretical investigations of something that relates the complexity of the measurement, but I'm not as familiar with that as I should be.
okay? So any more question? Okay, then let's thank the Professor Jarzynski for a very great talk.
Okay,
And
thank you.
I think, yeah, it will be very useful time for us to learn how to extend the laws of thermodynamics and entropy to the small systems. And I really appreciate your for preparing your talk and giving this wonderful lecture. Yeah.
Okay, and
So
thank you again for inviting me and for all of the interest and for all of the questions.